Hello, the following is a video over geometry, and this is the start of Unit 2 notes, okay, and this is called Geometric Transformations. And the first section, what we're going to do is we're just going to kind of do an overview of what a transformation is. So we want to determine if a transformation is isometric and identify corresponding parts of the preimage and image. And we want to be able to identify the type of transformation given a preimage and an image. So we've got this big underlying idea of transformations. We have rigid transformations and we have non-rigid transformations. So rigid transformations means that the size, remains the same. So the size doesn't change. Okay? Size doesn't change. Okay? And when we talk about rigid transformations, we would talk about reflections, translations, and rotations, okay? Non-rigid transformations is when the size changes. The size of a figure changes, okay? And we call that a dilation or a stretch, and we'll get into what those mean, okay? So let's kind of talk about what a transformation is. Transformation, by definition, is a one-to-one mapping of all the points on a figure to another figure in a plane. Okay? The original figure or input is called the preimage, and then the result of the transformation or the output is the image. So, basically what you have here, is you have these figures, and we either move them, we either, just slide them over, we reflect them, or we rotate, okay? And that's kind of where these, these things come in here. Reflection means that we mirror something. Translation means we just move something, and then a rotation means we rotate it. So let's kind of take a look at an example. And so what we have here is we have this thing called the preimage. Triangle STU has undergone a type of transformation called a rigid transformation to produce the image VWX. So the first thing that I want to show you, this, when it says here that the preimage, all right, that value means, when it says preimage, that's this triangle right here. Okay, this is the preimage. Preimage. And this is the original, okay? And then it says that it's gone under a rigid transformation to produce the image. So this is the image. And this is the result after transforming it. So this is the result of transforming it. Transforming, okay? And so what we notice is that also, with the way they name it, triangle S, okay, here's angle S, and V are in the same spot, okay? And what we can tell is that these angles here are going to be congruent, okay? Because all that's happened is we've taken this figure and we've just moved it over, okay? If we take point angle T, all right, we take that angle, and the next angle here is angle W. And the way that it's said there, because it's the second letter, we know that these two angles are congruent. All right, and the last one that we can tell is U, okay? So angle U, and I'm going to use 3 arc marks, corresponds with angle X, all right? And so I know that these angles are congruent, all right? And because it's a rigid transformation, that means that the size doesn't change. So angle S is congruent to angle V, angle T is congruent to angle W, angle U is congruent to angle X, okay? I can also come in here and I can say that these two segments, ST is congruent to VW, okay? I can also say that, TU is congruent to WX. And then I can also say that SU, that segment, is congruent to VX, okay? So what happens here is that we get this, we get a triangle here, and if I just take this triangle and I move it across, the size is going to remain the same. It's not going to get any different, okay? So let's go over here and let's check off all the measures that are equal here. So ST and VW, those are congruent, so this is good, okay? SU and VX are congruent, all right? And then TU and WX are congruent, okay? And then we can say that SUT is congruent to VXW, okay, this. So these are equal. The measures TSU and WVX are congruent. Their measures are equal. And then UTS and XWV are congruent. Okay, their measures are equal. Okay, so that's the idea. So rigid transformations means that your correspond. So let's just say this. Okay, a rigid transformation or an isometry, okay, is a transformation that preserves the size, length, shape, lines, and angle measures of a figure. The preimage and the image are congruent, okay? So a reflection, all right, does the same thing, preserves the size. A translation and a rotation all do the same thing. They preserve the size. Now, a reflection is like a flip, okay? It's like a mirror, okay? Whoops. Mirror, that's the word mirror. A translation, I think of the word slide, okay? And then a rotation, I think of a clock. Okay, I think of a rotation. Okay, all right, let's take a look at the next one. So here's what you've got. On this one, you have the preimage. This is the original. Okay, we can call that the OG image. And then we have the image. This is the result. Okay, so the question is that you know, what type of rigid transformation is shown? What we see is that corresponding angles are congruent and corresponding sides are also congruent, okay? And what we notice is that, you know, they're in the same position, you know? So I've got this length is congruent to this length. This is in the upper left corner, and so is this, okay? And that's the same thing with all the other congruent segments. They're all in the same location, okay? So it hasn't been rotated, it hasn't been mirrored. All that's happened is you've taken each of these points and you've just slid them in this direction, okay? So what we call that is we call that a translation, all right? So not too bad, not too hard to see, okay? Okay, the next thing that we can talk about is what's called a non-rigid transformation, okay? Non-rigid transformation is a transformation that does not preserve the size, length, shape, lines, or angle measures of a figure, okay? The preimage and the image are not congruent. So we have this thing called a dilation, and that's when all sides get changed. All sides are changed. Okay? And then a stretch is when only one dimension is changed. One dimension is changed. Okay? And you could say, instead of all sides, you could say all dimensions. Okay, length and width, dimensions are changed. Okay, so over here it says, you know, consider the transformation below. All right, so here's the preimage. Okay, we also call this the OG, the original. Okay, and then we get the image. All right, so we have this right triangle here. We have a 6, 8, 10 right triangle. And then what we've done is we've taken this triangle and we have reduced its size, okay? It's gotten smaller. So from here to here, it's gotten smaller, all right? So what we know is that the transformation is non-rigid, because the side lengths are not preserved. Okay, and that's the idea, okay? Because the side legs aren't preserved, then it's not a rigid transformation, it's non-rigid, okay? All right, on the next one, we're trying to determine what exactly this is, okay? We have our QRS, we have our preimage, okay, okay, which is also the OG image, and then we have our image, okay? Now, what we have to determine is what kind of transformation is this? What we notice is that, we've got R and R prime, we've got Q and Q prime, these little or apostrophes, we use the word prime, and then S to S prime. Now what we know is that, angle Q is congruent to angle Q prime, angle S is congruent to S prime, angle R is congruent to R prime, and their sides are also congruent, okay? So what we know is that the two figures are congruent, but we notice that S is not in the same position as S prime, okay? S is in the bottom right, okay, of this triangle, but all of a sudden S prime is pointed up here. So we have to figure out what kind of transformation is this? Is this a translation? Has it been slid? Has it been mirrored? Or is this what we call a rotation? And this is what we do call a rotation, okay? Mainly because it seems as though, all these points have just been moved around this point of this center of rotation, okay? We'll call this the center of rotation. All right, so we're going to take a look at a number of ways on how to identify what this becomes. Okay, let's jump in and take a look at what this means when it says prime notation. So prime notation is used to indicate that a figure has undergone a transformation. So when it says prime notation, what they mean, let's say you have point A, okay? And this is on the image, or the pre-image, okay? This is the pre-image. Let's come over here, right? Pre-image. Remember, that means the OG, and then you have your image, okay, after it's been translated. Okay? So what we notice is that from A, instead of calling it a brand new letter, we use this notation here to say here is the image, A prime. So A to A prime is this prime notation, and this arrow indicates a translation, okay? So, and that's what we can, what we can figure out is A corresponds with A prime, okay? CB would correspond to C prime, B prime, okay? And then angle ABC would correspond to A prime, B prime, C prime, all right? So we're just trying to go from the pre-image to the image and using some notation, and that's how we write it, using the prime, okay? All right, so, and I kind of use this idea here. It says a transformation maps a figure onto its image. So what we could say, all right, is that we've got triangle ABC, okay, and that is mapped, okay? And we say the word map, going from one to the other. Okay, so the arrow indicates a map to triangle A prime, B prime, and C prime. Okay, and so this is the notation that we would use to show a transformation. Okay, going from one, so here's the pre-image. Okay, here's the image. All right. And the arrow here, okay, indicates a mapping, okay, that we go from one triangle to the other, and this arrow indicates that they correspond with each other. This whole thing is a transformation, okay? All right. Let's take a look at the next one. Okay, it says that parallelogram DEFG has been rotated, okay? And so, if I were to write a mapping statement, then I would start here, okay? I would start with parallelogram or quadrilateral, just use kind of a quadrilateral symbol. DEFG, okay, maps to parallelogram D prime, E prime, F prime, and G prime. Now, the thing that I want you guys to see here is that D and D prime correspond. E and E prime correspond. F and F prime correspond. And G prime correspond. the order matters. Okay, so I'm going to say that down here, that the order matters. Okay, when you write this, all right? And that's how I know what corresponds with what. It depends on how you write it. So, you know, on this statement it says, which statement is correct? Check all that apply. Does point F map to point F prime? Sure does. Okay, it's the third letter here. It's going to be the third letter here. And we see that F and F prime share a common angle, okay, that those are congruent. So we know that that is true, okay? This is good. So let me circle that. Okay, and then it says parallelogram DEFG, okay, maps to parallelogram G prime, F prime, E prime, D prime. That is not true, okay? We want to show that D corresponds to D prime. That's why we put D prime as that value. So this is false. Okay, it says point D on the preimage corresponds to point D prime of the image. Okay, and again, yeah, let me write that in here, that this is the preimage. Okay, also known as the OG, not Q, OG. And then this is the image. All right, so this is true. Point D on the preimage corresponds to D prime of the image. Okay, and then it says that ED of the preimage, right here, okay, corresponds to G prime F prime. And it doesn't, okay, because it's not mapped to that. All right, DE corresponds to D prime E prime. All right, so this is false. And then the last one, parallelogram DEFG maps to parallelogram D prime, E prime, F prime, G prime. So I wrote that down originally, so that's got to be true. Okay, let's go move on. Okay, on the next page it says, which figure is the preimage and which figure is the image? So the preimage, all right, is always the one that doesn't have the prime symbols, okay? So what I would say is I would say quadrilateral, okay, JKLM. So JKLM is the preimage. Okay, and I'm just going to write that down here too. This is our preimage, also known as the OG image. And then if I were to say, I'm going to write it up here, I don't have much room, parallel or quadrilateral J prime, K prime, L prime, and M prime is the image. Okay, this is the result of transforming it. Okay, so this is the image. Okay, what is the mapping for this transformation? So I would say this. Okay, I would say that the mapping statement would be JKLM. Okay, after the mapping, we get quadrilateral J prime, K prime, L prime, and M prime. Okay, and then it says, is the transformation an isometry? And the thing that you have to realize is that it is. Okay, from J to M is 1.2, J prime, M prime is 1.2. JK is 1.7, J prime, K prime is 1.7, KL is 1.9, K prime, L prime is 1.9, and then 1.8, 1.8. Okay, all of the angles also are congruent to each other, so we know that it's a non-rigid, that it's non-rigid. So we'd say yes, it's a rigid transformation. Okay, sorry, I shouldn't say non-rigid, transformation. Okay, and then it asks, what type of transformation is this? And this is a reflection, and here's why, because there is a line of reflection here, okay, where J and J prime are just flipped over this line, M and M prime are flipped, same with L and L prime and K prime. So this is a reflection. Okay. All right. Okay. On this one, it says that hexagon A, B, C, D, E, F. Okay, is mapped onto hexagon A prime, B prime, C prime, D prime, E prime, F prime. And what we know, okay, is that this length here is 1, and it's congruent to all of these other lengths. Now that also means that all these lengths here are 1, 1, 1, and 1. Okay, and this 1, 1. 1 and 1 as well because they have the same congruent symbols, all right? But the one thing that has changed is AF has all of a sudden, A prime, F prime has become length of 3. So from 1 to 3, same thing with CD, okay? C prime, D prime is also going to be 3. These two are congruent. So it says, how can the transformation shown be described, okay? First of all, it's non-rigid, okay? Non-rigid means that it's not going to be the same size, okay? So I can say that it's not a non-rigid transformation. That's the first thing I can say. And that it's a stretch, okay? So if it's, number one, if it's a non-rigid transformation, I can get rid of the fact that it's a reflection, a rotation, or a translation, okay? And it's not isometric. Isometric means that it becomes the same, okay, that it stays the same. So it's a non-rigid transformation. The difference between me saying it's a dilation versus a stretch is because only one dimension here, one dimension is changed. Okay, and that's what we talked about with a stretch. Stretch means that one dimension has been changed. If these segments were also bigger, okay, then we would say that it's a dilation, but it's not because only one dimension has been changed, and that's this dimension, okay? So I can get rid of dilation as well. So hopefully you enjoyed this video. Go ahead and get started on the assignment, and we'll see you in a bit. Thanks. Bye.